general, every recursive implementation of a function has an equivalent iterative implementation. To add insult to injury, the iterative version is almost always faster than the recursive one, because MATLAB doesn't have to make multiple function calls with the associated overhead of creating the stack frames and copying input and output arguments back and forth. So why bother with recursive functions? Well, for many real-world problems, the recursive solution is much simpler conceptually, and consequently it's easier to implement. Let's see a fun example, the Sierpinski triangle, which is named after the Polish mathematician who invented it over 100 years ago. We're going to go into considerable detail with the Sierpinski triangle because it's a great way to gain a deep understanding of recursive functions, but it's also a very interesting shape. Here's an illustration from Wikipedia. It has the overall shape of an equilateral triangle, subdivided progressively into smaller and smaller equilateral triangles, as you can see here. Or you can look at it as very small equilateral triangles arranged to produce progressively larger and larger equilateral triangles. It's an example of a class of shapes called a fractal, meaning that if you zoom in, you'll see the same pattern repeating over and over. And here's its recursive definition. The base case is a Sierpinski triangle of depth 0, which is one equilateral triangle. The recursive case is a Sierpinski triangle of depth n, which is three Sierpinski triangles, each of depth n minus 1, arranged as shown here with one at the bottom left, one right next to it at the bottom right, and one on top sitting on the other two. This simple recursive definition produces elaborate shapes, and we can write a recursive MATLAB function to implement it. In fact, we've already written one for you. Let's take a look at it. Here it is in the editor window. Its file name is highlighted over here in the current folder window, and its name is sierpinski.m. And as you can see, it contains two functions, a main function named Sierpinski right here and a subfunction named Sier. I should warn you that we're going to analyze Sierpinski in great depth. In fact, before we're done, you might say that we're analyzing it to death. But stay with us. There's a good reason. As we said, it's a fun example, but it's much more than that. It's not only fun, it's a nearly perfect example for teaching you the power of recursion, the power to do very complicated things with very simple algorithms. It's also nearly perfect for showing how recursion operates simultaneously on multiple levels. And finally, it's perfect for demonstrating how recursion can turn on you and chew up computer resources. Akos and I want you to understand recursion, not just become acquainted with it, really understand it. And we're going to get you there with Sierpinski. Before we analyze it, let's make sure it works. The main function requires an argument specifying the depth. Let's try depth of 5. That looks pretty good. And let's try the minimum depth of 0. Just a simple garden variety equilateral triangle with a side of length equal to 1, which is the base case of the definition. And the next level up, which we get by calling Sierpinski with a depth of 1, gives us 3 equilateral triangles with sides equal to 1/2, arranged as we saw for the recursive case. One at the bottom left, one at the top middle, and one at the bottom right. Okay, it works. Let's analyze it. First, the main function is named Sierpinski, but it doesn't really do Sierpinski. It just sets the stage for its subfunction, Sier, which is the real star of the show, and then calls that function to perform the Sierpinski magic. That magic involves plotting hundreds or thousands of equilateral triangles, each one just the right size and in just the right position to produce the Sierpinski pattern. Let's go over what the main function does. First, it takes one argument, depth, but it doesn't do anything with it except pass it on to Seer down here. Next, it sets S, which will be the size of each side of the Sierpinski triangle, to be equal to 1. And it sets C, which will be the position of the center of the Sierpinski triangle, to be the origin of the figure axis, right over here. 0 for X and 0 for Y. Then it executes the clear figure command, CLF, whose job it is to prepare a nice empty figure ready for plotting. And it uses the axis function to adjust the plotting area so that the entire Sierpinski triangle will be within the field of view. And it includes the equal attribute so that what it plots won't be distorted. It uses the title command to display a title like this one, which it constructs with the sprintf command. And it uses hold on to allow multiple triangles to be plotted on the same figure. Then it calls Seer, which does all the hard work. And finally, it turns hold off in case the user wants to plot something else. And now let's see what Seer does. First of all, it takes 3 input arguments. The first is D, which is the depth of the triangle. The second is S, which is the size of one side of the triangle. And C, which is the position of the center of the triangle. Then it starts to work. First, like any good recursive function, it decides whether to enter the base case or the recursive case. You'll remember that rfact did that too by determining whether its input argument n was equal to 0. Well, Seer does a similar thing. It determines whether its input d is equal to 0. If d is equal to 0, the base case is run. And that base case simply calls the plot function to draw just one equilateral triangle of size S centered at C. I would invite you to study these arguments to plot on your own to convince yourself that these arguments do in fact produce an equilateral triangle of size S centered at C. If D is non-zero, then the recursive case is run. The job of the recursive case is to draw 3 Sierpinski triangles arranged like these 3 ordinary triangles, here, here, and here. We might call them sub-Sierpinski triangles, because together they make up one full Sierpinski triangle. The size of each of these 3 sub-Sierpinski triangles is set to 1/2, so that they will just fit inside the full Sierpinski triangle of side equal to 1, which is the value of S that was input to Seer. So the first step in the recursive case is to cut S in half. Next, the height of the subtriangle is calculated. And then 3 recursive calls are made. That will produce 3 Sierpinski triangles at the positions indicated in these comments. Bottom left, here. Top middle, here. Bottom right, here. To do that, each one must be shifted relative to the center of the full Sierpinski triangle. Down and to the left, here. Up to the middle, here. And down and to the right, here. And I would invite you to stare at these 3 shifts, here, here, and here, to convince yourself that they do just that. And by passing itself the correct sizes and positions, that's all Seer needs to do to plot the 3 sub-Sierpinski triangles correctly. But I've left out what might be the most important parameter in each one of these recursive calls, the first one. This first parameter doesn't have anything to do with the size or the positions of the subtriangles, but it's very important because it determines how many triangles will be plotted within these subtriangles by determining how deep that recursion will go. The depth is reduced by 1 for these calls, as you can see. and it will be reduced again in the next level of calls, and so on. And all the calls that receive a depth of 0 will run the base case. And we'll plot one equilateral triangle with no recursive call. In fact, notice that we never call plot in the recursive case. Each triangle is drawn in the base case. Okay, it took me a few minutes to say what SEER does. Still though, I don't know about you, but it's amazing to me that these 11 lines of code can produce something so complicated and, dare I say, beautiful. Okay, fair enough. Sierpinski was no Michelangelo or Wang Ming. He wasn't an artist at all, but you gotta admit he came up with some pretty impressive drawings. Let's see another one. This picture looks like a big triangle with smaller triangles inside it, and smaller triangles inside them. But in fact, it comprises only the smallest triangles, and their placement in the figure forms the larger triangles. If you want to see the order in which the triangles are drawn, we can put a breakpoint on this line in our base case where we call the plot function. Before I do that, though, I'm going to insert one line temporarily right here before the call to SEER. It'll draw a red outline of the entire Sierpinski triangle, so you can see where in that big triangle each little tiny triangle is plotted. Okay, let's put the breakpoint in. And run it. And now let's click Continue. And there's the first little triangle at the bottom left. And I'll click a second time and a third time. And now we've seen SEER draw 3 little triangles. Of course, each one was drawn in this base case, which is executed when the depth D is 0. And these 3 depth 0 Sierpinski triangles, taken together, form one depth 1 Sierpinski triangle. The next 3 clicks will give us 3 more depth 0 triangles for a second depth 1 Sierpinski triangle. And 3 more will complete a third depth 1 Sierpinski triangle. Together, these 3 depth 1 Sierpinski triangles form a depth 2 triangle, and so on. At the lowest depth, which is 0, the order is bottom left, top middle, bottom right. And at the next depth, which is 1, the order is bottom left, top middle, bottom right. And this depth 2 triangle is the bottom left part of a depth 3 triangle, which is the bottom left part of the whole depth 4 triangle. And this depth 2 triangle comprises 3 depth 1 triangles, each of which comprises its own set, 1, 2, 3, of depth 0 triangles. It was drawn because SEER was called once in the main function with its first argument equal to 4, and then once inside itself in this first recursive call with its first argument equal to 3, and then once again in this first recursive call with its argument equal to 2, and then 3 times here, here, and here with its argument equal to 1, and finally 3 times here, 3 times here, and 3 times here with its first argument equal to 0. So SEER has already operated at 5 depth levels from 4 down to 0 to draw these triangles. And it shows you that in a recursive function, The order of things is not the simple line-by-line order that we are accustomed to for non-recursive functions. Well, it is, but with a recursive function, a single line may be operating simultaneously at many different levels in the recursion. So you have to think, and think hard, which is exactly why I like recursion. To encourage you to think hard about recursion, I'm going to let you watch it draw an entire depth 4 triangle, one tiny triangle at a time, from beginning to end. And instead of pounding on the continue button over and over, I'm going to clear the break, quit debugging, and just slow things down by inserting a pause of 2/3 of a second right here before the plot statement. And here we go. It has a nice 1, 2, 3 rhythm, like a lullaby. In fact, I'm getting kind of sleepy watching this. Hey, I don't know whether watching Seer draw its triangles one by one helps you understand recursion or not. I think it helps, and I hope it does. But if it doesn't, at least it might help you if you have trouble falling asleep. So back in the code over here, in order to draw all these triangles, the main function Sierpinski calls Seer just one time, passing in the value 4 as a depth. After which Seer makes 3 depth 3 recursion calls, here, here, and here. But here's an interesting question. How many total times is Seer called before this second depth 3 call? The immediate reaction might be 2. The first being the original depth 4 call here, and the second being the first depth 3 call here. But that ignores the fact that this first depth 3 call draws an entire depth 3 Sierpinski triangle at the bottom left. And in order to do it, it makes 3 depth 2 calls, and each of those 3 depth 2 calls makes 3 depth 1 calls. And each of those 9 depth 1 calls makes 3 depth 0 calls. And those 27 depth 0 calls finally plot the tiny triangles. If you count them out, that's 41 calls of Seer before we get to the second depth 3 call here. And then this second depth 3 call draws another entire depth 3 Sierpinski triangle at the top middle, which requires 40 more calls. And then finally, the third depth 3 call draws the third depth 3 Sierpinski triangle for a grand total of 121 calls to Seer to draw the full depth 4 Sierpinski triangle. That's a lot of calls of Seer in one execution, considering that the code has only 4 calls, 1, 2, 3, 4, and no loops. To see the depth 3 Sierpinski triangles appear in the order that they're drawn, I'll get rid of the pause and save the file and put a conditional break at the beginning of Seer. I'm going to make it stop when d equals 3. Okay, let's input 4 to Sierpinski one final time. Okay, we're waiting at the conditional break. And we can see in the workspace over here that D is equal to 3. So we're ready to draw a level 3 triangle. When I hit continue, it appears. Then I hit continue again, and the second one appears. And when I hit it again, there's the last one, and there's our level 4 Sierpinski triangle, comprising 3, 1, 2, 3, level 3 triangles. Okay, let's remove the break. I just click twice on it. And let's run Sierpinski with a larger depth, say 7. Ooh, lots of detail there. Now we can look at that detail by coming up here, hitting this little plus sign, and then clicking, 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 and we see all those little tiny triangles. If I click home, we go back to where we were before. If we go even deeper, let's do 8. MATLAB slows down quite a bit. It takes a lot of CPU time. Let's see exactly how many seconds. You can look up the function CPU time, but it just returns the total CPU time the MATLAB has used since you started it up. Over here in the workspace, you can see that T0 equals 213.38, meaning that from the moment I started this current MATLAB online session until just before I called Sierpinski here, it had used 213.38 seconds of CPU time. And to get the time for the command itself, we just call it before and after and subtract. Okay, it's time to wipe all this stuff off my command window. And I'll clear the workspace too. This relatively long 7.54 seconds of CPU time was required because Sier was called thousands of times. To figure out how many times, we note that for a call at a depth of D, the number of calls to Sier is equal to 1 plus 3 plus 3 squared plus 3 cubed plus 3 to the 4th power and so forth, all the way to 3 to the 8th power, if D is equal to 8. That can be written formally this way. And we can calculate this sum for D equals to 8 in one statement. And if you're good at summation formulas, you can work out this formula for the sum. And we can check it with MATLAB for D equal to 8. And we get the same number. So the formula checks out. Either way, that's 9,841 calls of Sier. And each call produces one Sierpinski triangle, including the biggest one, all the intermediate ones, and all the tiniest ones. So in this figure, you can see 9,841 triangles, even though only a subset of them were actually plotted, the tiniest ones. And how many of the tiniest ones are there? Well, since only the calls at the deepest level actually call plot, the number is 3 to the 8th power. 6,561 tiny triangles, which is approximately 2/3 of the 9,841 calls to Sier. You'll remember from our study of the stack with rfact that for each of these 9,841 calls, a frame is added to the stack. And when the called function returns, the frame is popped off the stack. You may also remember that with rfact, the stack reached a height equal to the number of calls. For Seer, however, the situation is much different. For the case we're looking at, with 9,841 calls of Seer resulting from an original call with a depth of 8, the stack reaches a maximum height of just 9. Whenever it reaches that maximum height, the latest instance of the function returns, and its frame is popped off the stack before the next call. The maximum stack height for Seer is always equal to 1 more than the value of its first argument, d. And the maximum height for rfact is always equal to 1 more than the value of its first argument, well, its only argument, which is n. The functions are similar in that regard. The reason that the stack got so tall with rfact was that the inputs we gave it were so large, like 69,898, which caused rfact to issue 69,898 recursive calls. When you give rfact an argument of only 8, the maximum stack height is only 9, and the total number of recursive calls is only 8. When you give Seer an argument of only 8, the maximum stack height is also only 9, but the total number of recursive calls is 9,840. So what's the difference between rfact and Seer that causes so many more recursive calls in Seer than in rfact? Well, the difference is that rfact executes only one recursive call in the recursive section of its code, whereas Seer executes 3. 1, 2, 3. When there's just one call, the number of recursive calls will increase by 1 when the level of recursion increases by 1. If 2 recursive calls are executed, the number of recursive calls will double when the level of recursion increases by 1. If there are 3, as there are for Seer, the number will triple, and so on. For functions like rfact with just one recursive call in the code, the number of calls increases linearly with the depth of recursion. For functions like Seer with 2 or more calls, the number of calls increases exponentially, which means that it will increase not by a fixed amount, but by a fixed factor. By the way, I don't know about you, but I'm getting very tired of reporters and commentators trying to sound smart by using words they've heard actual smart people use, like exponential, when they're in fact just guessing what the words mean and guessing wrong. Here's a good example. Forecasters fear that the destruction of just one large oil field in Saudi Arabia could cause the world's oil prices to increase exponentially. It'd be so nice if they would just try sticking to words they understand, like oil prices can increase a whole lot. And if that doesn't sound smart enough, they could say increase drastically or dramatically. Increasing exponentially means something specific, namely increasing by a constant factor, or at least a relatively consistent factor. The factor can be 3 or 2 or 1.01. It just has to be greater than 1, and you have to have some sequence of 3 or more values. One jump in a value can never be exponential, no matter how big it is. Exponential growth is very common in recursive operations, and it always has the same upward curving pattern. We can see it in a plot of CPU time versus depth for Seer. Let's get some CPU times to plot. Here I'm making one throwaway call to Sierpinski before I start timing things. I'm doing that because MATLAB often does some setup on the first call in a sequence of calls of the same function. We don't want that setup time to count in one call and not in the others. After the setup is done, the for loop calls Sierpinski with progressively larger and larger depths, storing the times in the vector t. I'm going to hit return. Well, I'm not going to make you wait for this. Let me fast forward time for you a little bit. Okay, now let's plot t. And I'm going to turn the grid on. This is just the sort of curve you'd expect when times increase exponentially. It starts out increasing, slowly, but at the end it is really taking off. From the shape of this plot, you can see that exponential growth can slow things way down. And I'm going to prove that to you by doing something that we recommend that you don't try at home, especially if you're using an installed version of MATLAB. Usually we encourage you to do everything that you see me do, but not this time. If you do what I'm about to do, you're going to be sorry you did. For one thing, you're going to hang up MATLAB. If you do what I'm about to do with an installed version, you'll probably have to reboot your computer. Sounds like clickbait, right? You're not going to believe what happens when Mike Fitzpatrick does this. But in this case, I'm serious. You might even lose some work, so don't do it yourself. Just watch me do it. As we pointed out in our introductory course, we're professionals. And by the way, I do all my own stunts. And here's what I'm going to do. I'm going to set my computer on fire. Okay, ready? Well, just kidding. I'm not actually going to set any computers on fire. But I am going to increase the temperature of the computer that my session of MATLAB Online is running on, wherever it is. I can assure you of that, because it's about to get very busy. I hope its fan is working, because I'm going to run Sierpinski with a depth of 12. Last warning, don't do it yourself. Here goes. Well, here again, I'm not going to make you wait. I'm going to skip you forward in time a few minutes. And we're back. As you can see, increasing the depth by 3 increased the time a lot, a whole lot. A depth of 12 required 507.78 seconds. That's about 8.5 minutes. And that's a long time. I know, I had to sit here and wait for this thing to finish. And it hasn't finished yet. Because if we zoom out, we can see that we're still waiting for the triangles to be plotted. Why does this thing take so long? Well, first off, since there are 3 recursive calls in the code, we would expect to see an increase in the CPU time by a factor of 3 for each increase in the depth of 1. Well, we've increased the depth by 3, so... Okay, this is what I was warning you about. We've crashed MATLAB. Or as this message says, there was an issue with MATLAB. Well, the issue is that MATLAB could not plot the triangles, and it recommends that we contact technical support. Well, that's not so easy for you, but it is very easy for me because I have a MathWorks guru on call. So I've done that for you. I paused my recording session and contacted him. And he said that the problem is that MATLAB's graphics system, while it can do extremely complicated plots, is not designed to handle this many plot calls in one application. How many plot calls is too many? Well, he didn't say. But applying our formula of 3 to the 12th power gives 531,441 triangle plots. And so we know that's too many. The hang-up occurred while the figure was being updated after Sierpinski had done all its work, generated all its plotting instructions, and returned. The display system then tried to process all those plotting instructions, and that's when MATLAB crashed. Well, that's an explanation, not a solution. So is there a solution? Yes, there is, and we'll show it to you in a few minutes. But in the meantime, let's get back to our analysis of this exponential growth. As I was saying when the lights went out, since there are 3 recursive calls in the code, we would expect to see an increase in the CPU time by a factor of 3 for each increase in the depth by 1. And we've increased the depth by 3 beyond the last point in our plot. So we would expect to see the time increase by 3 times 3 times 3, which is a factor of 27, relative to the 19 seconds shown in the plot for the depth of 9. And that's very close to what happened here. The elapsed CPU time increased from about 19 seconds to about 508 seconds, a factor of 26.7. Okay, time to clean up again. And let's close the figure too. And I've cleared the editor window too, so we have a clean slate. Okay, it's time to fulfill our promise to show you the solution to the crashing problem. The solution is provided in this M file, which I've added over here. It's called Sierpinski E.M with an uppercase E at the end, which stands for efficient. We'll double click it. And before I explain it, I'll run it. Not bad, huh? Instead of 507.78 seconds, it took 1.56 seconds. And as an added bonus, it actually plots. And just to confirm that there is an actual full Sierpinski triangle here, let's zoom in on the thing. As you zoom in, it just looks like you're seeing a bunch of copies of the same thing that you saw before we started zooming. But eventually, if we get in close enough, and by the way, I'm zooming with the scroll wheel on my mouse, you can finally distinguish the individual tiny triangles. And you can also believe that this function did draw 500,000 of them in a second and a half. So what's the difference? Well, for openers, Sier does no plotting. None at all. Only the main function now calls plot. Up here, where it's always plotted the outline, and down here, where all 500,000 triangles are plotted in just one call to plot. The approach this time, which is based on a version that Akos created, is that Sier just calculates the points that need to be fed to plot, instead of plotting them, and returns them as an output argument, PTS. PTS stands for points, and it's a 2x(n) array of points in which the x values are in its first row and the y values are on its second row. When main gets its hands on those x and y values, it passes them directly to plot, which plots the entire Sierpinski triangle. Akos's approach takes advantage of the fact that plotting is far more efficient both in execution time and memory space when everything is plotted at once. The same figure takes far longer and far more memory when many individual features are plotted one by one in individual calls to plot. But the downside of this approach is that you don't get to watch the triangles appear one by one in rhythm with Brahms' lullaby. But the need for that actually turns out to be surprisingly rare. Let's look at Sier's base case. Let me close the figure so we can see all of it. In the base case, instead of plotting a triangle, the x and y values are calculated for the triangle, here and here, and then appended to a set of points that were passed in as the fourth argument to Sier when it was called. Those points were calculated in a previous activation of Sier, except for the case in which the main function was the caller. The main function doesn't do any calculation of points, so it just passes in an empty array for that fourth argument. If you examine Sierpinski and Sierpinski E closely, you'll see that the 4 values for x and the 4 values for y plotted in the base case of Sierpinski are exactly the same as the x and y values appended to the points array here. But here in Sierpinski, a value of NaN is added after the last x value and after the last y value. These not a number values serve as a signal to plot not to continue the line from the end of one triangle to the start of the next. You can look that feature up in the help page for plot. It's way down at the end. And now let's look at Sier's recursive case. The first call gets the points that were input up here as its fourth argument. And then it does its work, which is to append all the points for its Sierpinski triangle of depth d-1 to the points that it received and return the result. That result is assigned back to PTS. Then the second recursive call gets as input the set of points that were just returned by the first recursive call. It appends the points for its own depth d-1 Sierpinski triangle to those, and its result is also assigned back to points. Finally, the third call does the same thing. And as a result, PTS now contains 3 depth d-1 Sierpinski triangles, which together make up one depth d Sierpinski triangle. Nothing has been plotted, not one triangle, not one point in one triangle, but all the points for all the tiny triangles that make up a depth d triangle are right there in the output argument PTS. The speed up with this plot everything at once approach is enormous, but that doesn't affect the shape of the growth curve. The number of recursive calls is still going to increase exponentially with increasing depth, and so is the execution time. Let's plot the time for depths from 1 to 14. I'm going to speed you up a little bit here. There. Here again, it starts out increasing very slowly, but then begins to accelerate and really takes off at the end, just like any good exponential growth. So both the plots that we've seen have had the classic exponential form, but there's a big difference in their time values. The first Sierpinski function hit 19 seconds at a depth of 9, and this Sierpinski E version is much less than 1 at a depth of 9, and comes in at less than 14 seconds for a depth of 14. Well, I'm almost done with this Sierpinski E function, but there is one last detail to deal with, and that's bad input, which is to say negative or fractional depths, either of which will send this function into infinite recursion. We could handle those cases in the same way that we did with rfact, by checking the inputs and quitting if they're bad, but there is a simpler way. Just change the base case from d equal to 0 to d less than or equal to 0. I'll let you play with that. All right, I'm going to clean up. And congratulations, you have made it through our entire analysis of Sierpinski triangles. And I hope you can now appreciate how simple recursive code can yield complicated results and how it can operate on more than one level at a time, and how it can gobble up computer time with exponential growth. If you now appreciate these 3 ideas, then you understand recursion, really understand it, and our job is done. And you've even learned a little something about how to plot quickly. Looking back to our first recursive example, the factorial, you'll remember that after we finished a thorough examination of the recursive calculation with rfact, we showed you how the calculation can be done more simply with an iterative version. If you're hoping to see us do that with Sierpinski, you're going to be disappointed, because Sierpinski is an example of a calculation for which the recursive version is far simpler than any iterative version. In fact, that's another reason we chose it as an example. We're not going to show you an iterative version. In fact, I don't even know an iterative version. It would be very painful to try to figure out all the correct coordinates of all those thousands of tiny triangles with loops. It can be done, I can assure you of that, because it can be proven that any recursive function can be done iteratively. But writing the iterative version is not worth the effort. And that alone should convince you that learning recursion is worth the effort.